and just give you a little bit of a summary of what we have done, and then confront you with another little problem. So what we have done with this pH is, so far, we have looked at the pH of a strong acid. And we said the strong acid usually completely dissociates in water. So complete dissociation, that's the definition of a strong acid. And when this is the case, we can very easily calculate the pH of this solution, because we know that pH equals minus the log of the acid. Yeah? Because the concentration of the acid that we put in is the same as the concentration of the protons that we get. So that is one equation that I want you to remember, or I should say pH equals minus log of the protons if we have an acid that produces 2 protons. Yeah? And we've done a little bit of an exercise where we have, for example, sulfuric acid, which produces 2 protons, so we have to take that into consideration when we calculate our pH. So that is when we have a strong acid, we whack that into water, we can easily calculate the pH of that. We then said, right, what happens if we have a weak acid and its conjugate base plus the conjugate base? So if we put these two things together, we get, bless you, a buffer. We get a buffer, exactly. And these buffers are very, very important because they can stabilize the pH to a range that we exactly want. So buffers are extremely important for biological systems. And you should never do an experiment that doesn't contain a buffer. And for these buffers, we said we have this famous Henderson-Hasselbalch equation. So whenever you hear the word buffer, and it's not related to a train, use the Henderson-Hasselbalch equation. And this is pH equals pKa minus log of the acid concentration divided by the base concentration. Yeah? This is the Henderson-Hasselbalch equation. You can also write this in a slightly different form, which is exactly the same thing. It says it is the same equation, pH equals pKa plus log base over acid. Exactly the same. You don't have to learn both. One is enough. And it just simply depends which version you prefer, the minus log or the plus log. But you can apply both equations equally to whatever problems you have with buffers. Okay? So that was good. Let's quickly remind ourselves what this pKa is. We said if we have, say, a reaction with an acid, and this dissociates into proton and the conjugate base, that's the conjugate base here, to this acid. Remember, a conjugate base only differs by the proton from the acid. So the acid has the proton, the base here doesn't have the proton. We wait long enough for this reaction to happen, to stabilize itself. Then we can write the equilibrium for this. And this has an equilibrium constant, which, as the name says, is constant, shouldn't change, although this constant is dependent on the temperature. And we said Ka equals the concentration of the protons times the concentration of the base divided by the concentration of the acid. That's what's left. That's why I write it as what's left in the equilibrium. Yeah? Once this equilibrium, once everything has established itself. And we said, if the Ka is small, then our acid is weak. Acid is weak. If the Ka is large, then our acid is strong. Yeah? That is, bless you, where we sort of left it. And we can, because if an acid is weak, then Ka will be, say Ka equals, say, I just make something up, 10 to the minus 5. And because chemists and biologists don't like these exponents, minus 5 something, they introduced this notation of pKa, and the pKa is defined as minus log of the Ka. So in this case, what would be the pKa? Loud? Was right. I don't know who said it. Go on. It's 5. Yeah? Log Ka, log of 10 to the minus 5 is minus 5. Minus times minus is positive, so here the pKa, in this case, would be 5. And the larger the pKa, the weaker the acid. Bless you. Most organic acids are in the range of pK2 to pKa 9 or something like that. So pKa2 is a strong, weak acid. Can you say that? Strong, weak acid. You know what I mean. Whereas pKa 9 would be a weak acid. Yeah? We can also do something else where we have, say, the conjugate base. We put that into water. And this now gives the conjugate acid plus what else? Yeah, loud? Somebody said? Hydroxide, exactly, OH minus. So we don't have any protons in here, but we can, again, write this as an equilibrium. And this time, because we produce an OH minus, which is a base, we call this Kb. We can write the equilibrium. We have Ha times OH minus divided by H minus, and usually this H2O, this concentration here, we ignore that or we hide that in this Kb here. So usually we don't write that down. It's a bit naughty, but hey, let's be naughty. And again, what we can do is we can define a pKb for that. And a pKb is defined as minus log Kb. The same rule applies small pKb, strong base. One thing that I want to share with you, but I don't really want to explain because people get terribly confused, is the following. If we have the pKa of an acid plus the pKb of the conjugate base, so that's the pKa of acid plus the pKb of the conjugate base, and if we add them together, something absolutely miraculously appears. Because they both, added together, give a magic number. Yes! Exactly. It is 14. And I want you to remember that. pKa plus pKb is always 14. It doesn't matter what acid or base we use, it's always 14. And we had something like that before when we looked at a special case, when we looked at water, where we said pH plus pOH is also 14. So I want you to remember that. pKa and pKb, always 14. pH plus pOH, always 14. So if I give you, for example, a pKa of 4.75, you can immediately calculate the pKb. The equilibrium constant for the base. If I give you a pH, say pH is 9, you can immediately calculate the pOH, which would be 5. Yeah? So you can interconvert these things. So we had a strong acid, we had a mixture of acid and base. But what about if we just have a weak acid? Weak acid. Now the problem with a weak acid is we can't really, we need to know what the pKa is because this weak acid doesn't dissociate very well. It just sits there, hands in its little pocket, and says, nah, not dissociating. Not today. Maybe on Friday. Yeah? How can we calculate the pH of a weak acid? And there's a special equation which I want you to remember. This equation is pH equals 1/2 of pKa minus the log of the acid concentration. I could show you how we get to this equation, but frankly, I don't see any point in doing that because within 10 minutes you've forgotten it, how you get to that. Not because, you know, you're like unlike my cat. My cat is so intellectually challenged. He is so dim that I would call him the black hole under the dim cats. In his presence, even the sun stops shining. And I know it's not very nice, but he's really stupid. And I'm not saying that you are stupid. It is just simply, why should you learn something that's of no relevance to you if you've got the final result here? Yeah? If people want to know how you get there, let me know and I'll show you. But, you know, life is much easier if you don't know everything. That's the first rule of mafia. So, what can we do with this equation? Let's do an example. We know that acetic acid or I tell you, acetic acid has a pKa, of 4.75. So it's not a terribly strong acid. Well, actually, it is a weak acid. And I have a concentration of 0.1 molar. What is the pH of this solution? What's the pH of this solution? Can you try to figure out? So pH equals 1/2 of 4.75 minus log of the acid, and the acid always has to be in the form of molar. So if we have millimolar or something like that, then we would have to convert that into molar. But luckily, in this case, it is molar already, so log of 0.1. Because that sits in the bracket, we have to calculate that first. So what is log of 0.1? Log of 0.1? Minus 1. So we have 4.75 minus negative 1. 4.75 minus negative 1 gives? That gives 5.75. Yeah? And half of 5.75 is 2.875. So that would be the pH of our weak acid. Yeah? Now let's compare that to the pH if we have a strong acid, HCl for example, bless you, and we have a concentration of 0.1 molar. Can you calculate the pH of that? pH equals, in this case, minus log of the acid, pH equals 1. Okay? So, in the case of the strong acid, with the same concentration, we have a pH of 1. In the case of a weak acid, we have the pH of 2.875. When do we actually talk about a weak acid? When do we know which equation we have to use? Usually, you use the weak acid equation, you use this equation here, you use this when you've been given a pKa. So when you have a pKa, and this pKa is, say, larger or the same as 2. So if you have a pKa given, and this is larger or equal to 2, then you use the weak acid equation. If you don't have a pKa, then you assume it's a strong acid, and you simply use this equation. Yeah? Bless you. And I just want to give you a little application what you can do with this weak acid thing, with this weak acid equation. Sorry? Just a quick application. Let's assume we have an acid. Let's assume we have acetic acid again. We know the acetic acid pKa is 4.75. And I measure the pH of a solution. I do not know the concentration of this acetic acid. So I have no idea what the acetic acid concentration is. It happens all the time in the lab. you have a bottle and it says acetic acid on it. And you check that it's acetic acid, so you open the lid, you take a sniff, you almost keel over backwards because it's so strong. So yes, it is acetic acid, and you stop crying. But you have no idea what the concentration is because the project student forgot to label it. What can we do? Well, what we can actually do is we can use our equation, because we are clever. We use this equation, pH equals half of pKa minus log concentration. And we simply measure the pH of this guy. So we find that here the pH is, say, 3.4. So all we need to do is we really need to arrange this equation here, our weak acid equation, and we need to find C. So what do? First of all, we try to get rid of this half, so we multiply both sides by 2. And we get 2 pH equals pKa minus log C. C is the concentration of our acetic acid. And then I just simply rearrange this equation. I bring the log to that side, I bring the pH to that side, and I get log C, so the minus has disappeared because I bring it to the other side, equals pKa minus 2 times pH. So our pKa was 4.75. Minus the 2 times 3.4. So we have 4.75 minus 6.8. And that's roughly minus 2. Is that right? 4.8 minus 6.8 minus 2, negative 2. So I know that my log C equals minus 2. How do I find out C? Loud? 10 to the power of. Then we get 10 to the power of log C equals 10 to the power of minus 2. 10 and log cancels out. And we get C equals 10 to the minus 2. And we know that when it comes from a logarithm, the unit is molar. So our acid concentration in this case, the acid concentration in this was 1 times 10 to the minus 2 molar. Simples. Does it make sense? So by just using the pH and knowing the pKa, I can calculate what my concentration is. Sometimes it is not easy to find, if you have a new substance, you know it's an acid, How do you know it's an acid? I give you a substance. It's a white powder. How do you know that it is an acid? You put it in water, you put an indicator in, and if the indicator shows that it changes color, for example, and that's, you compared it to what it does with a true acid, it shows the same color, well, then it's an acid. How do you find out what the pKa of this is? Well, we have our equation. We have pH equals half of pKa minus log concentration. Now, you use a known concentration. So you take this, weigh in a certain amount of water. So you know your concentration. You measure the pH of that. And what you can find out with this is the pKa. So as long as you have two of these things, you can find out the third one. And this method is actually used if you want to determine the pKa of an acid, of a weak acid. And also, quite nicely, if you know the pKa of the acid, you then can very easily calculate the pKb of the conjugate base. So you get a lot of information from this. Does that make sense? I'll give you a few exercises as homework, and you can practice. And if you don't succeed on the first attempt with these homeworks, you know the phrase, if you don't succeed on the first attempt, then parachuting is not for you. Yeah? But if you don't succeed in this homework, that's fine. That's absolutely okay, bless you. That's absolutely fine. Because, and I showed that people yesterday in the drop-in session, you know what fail stands for. What does fail stand for? The people I showed yesterday thought, first attempt in learning. Yeah? So please do fail. I want all of you to fail. Okay? Happy with that? Please do fail. No, yes. Because if you fail, you learn something. Clever people, no, stupid people make the same mistake twice. Clever people think about new mistakes that they can make. Right? So fail.